So this is going on page 32 when we're done. So you should know that a radical is a square root. It's like the big boy and girl way to say square roots, because we use the proper language now. So this square root sign is also called a radical sign. And what's underneath the radical is what's called the radicand. Pink. So, think before you speak here. If x squared equals 25, then what is x? I love when I say think before you speak and the hand goes up. Go ahead, because I bet you're wrong. Wrong. Even worse. He wasn't actually wrong. He just wasn't complete. No, what? What is the square root of 25? But you can simplify that.
X equals 5 squared?
No, because that would be 25. There's no radical sign left. Well, hey, let me ask you this. Hang on. Is 25 a perfect square? Yes. Okay, so to solve this, you would take the square root of both sides, yes? Since it's a perfect square, there's no square root sign left. But when you find the square root of a number, aren't you finding the number that times itself gives you that number back? So 5 times 5 gives you 25. So he just wasn't complete because his arm shot up and he didn't actually think. Like I said, think before you speak. No. There you go. X equals plus or minus 5. There are two things that when you square them give you 25, and that negative answer is super important. This is a quadratic, so it is possible that we get two answers, and we do, in fact, get two answers. You cannot ignore the negative one. That's important. There are times where we might take the square root of something when we're solving it, and we only need the positive one. If x is the side length of a triangle, then a negative number does not make sense. If the side length of the triangle is an expression, and when you plug negative 5 back in, you get a positive answer, then negative 5 is one of your solutions. Okay? So you have to check both of them. If you have two answers, they may both work. You cannot ignore the negative part of that. Does that make sense to you? Okay, now, the difference between this then, if it wasn't something I was solving, because this is an equation that I'm solving, if I just said, what is the square root of 25, the answer to that is 5, because that's a principal root. And there's a complicated, well, not real complicated, but there's a long explanation behind that that we don't have time for. I did figure out a few years ago, though, that nobody ever actually teaches you square roots. They don't teach you that stuff. You just start using them. Just all of a sudden one day when you're doing Pythagorean theorem, you just start using them. But they never really explain to you why it's plus or minus besides the fact that you can square the negative and whatnot. And why it's different when it's just the square root of 25 by itself. So just know that when you're solving it, there are two answers. And that's usually what's going to happen with you anyway. But just plain old square root of 25 by itself, the answer is just 5 because it's called a principal root. You get into that a little bit more in your advanced math, but make sure you know the plus or minus thing here. Okay, so then when x squared equals 26, tell me the first thing I should write down. Plus or minus. So x equals plus or minus something. Is 26 a perfect square? No. Do I want a decimal? No. So your answer is the square root of 26, or plus or minus the square root of 26. It is what it is. You can't do anything else. All right? Now, should you have a basic concept of what that value is? Yes, and I don't mean estimate it by hand or use a calculator or anything, but you know that 26 is between two perfect squares, which is 25 and 36, right? So that value has to be somewhere between 5 and 6, and is it closer to 5 or 6? 5. So it's 5 point something, right? And that just at least gives you an idea of whether or not your answer is reasonable. Reasonableness of an answer is an important thing too. So make yourself a little note here that you should have no decimal answers. When you simplified the square roots in Algebra 1, there weren't decimals because that's the whole point of simplifying it. When you did Pythagorean theorem, whenever it was that you did it, because y'all are in different grades, your teachers may have had you type stuff like that in and get a decimal, but those days are over. We are super concerned about exact answers. Exact answers and accuracy, very, very important. So this is an exact answer, okay? But if you were doing some measurements and you're trying to figure out how long you need this board to be, and you go to Home Depot and you say, all right, I need y'all to cut me this board and I need it to be the square root of 26 feet long. They're going to look at you like you're crazy, right? So that's an exact answer. Your Home Depot answer would be your 5-point whatever answer, right? And so if you were going to go buy a board and cut it yourself, you would at least know it's got to be longer than 5 feet or it's not going to fit. Does that make sense to you? So, but this is exact, and we always keep everything exact as long as we possibly can, and most of our final answers are exact. And when they're not, the work stays exact all the way until the end, or you have rounding error. And then you might have done all this process that you understand, that you did well, but then you get it wrong because you didn't, you rounded too soon or something, okay? So we're going to look at simplifying. Now, there's different ways to do this. You may have you came from different teachers in different places, so, you know, we could have all learned it maybe, I don't know, 4 or 5 different ways. I'm not saying that you have to do it my way, 100%. There are parts of it that you're going to need to. But if you never really got it or you're struggling with it, then I would suggest doing it this way. Of course, the reason I'm doing it this way is because my personal opinion is that it is the best way. But I usually come about those opinions because I've done this for so long. It's what usually makes sense to the kids the most. So some of you might already be at the point where you're taking the shortcuts and you can look at them and just know most of them. But even you are going to need to listen to what I'm saying because they're not all going to be small numbers that you can actually do that with right now. Right? So in order to be able to, regardless of your way of doing it, in order to be able to simplify them, you need to do something that you learned in elementary school, which is prime factorization. Okay, so we're not even talking about radicals right now. In elementary school, when you started looking at numbers and how they relate to each other, we'll start with like a 45. You would look at what the factors of 45 are, right? Now, because it's prime factorization, even though 1 times 45 works, that's not prime factorization because 1's not a prime number. Okay, so we don't care about that one. But you start by just what are 2 factors of 45? I just said we don't use 45 and 1. But besides that, I heard 5 and 9. Okay, so I'm going to write down 5 and 9. We're making a little factor tree. And as you go down your tree, once you get to a prime number, you put a circle around it because it ends that branch. Okay? Then we've got 9, and that's 3 and 3. Okay, hang on, back up. From the beginning, I could have used 15 and 3 instead of 5 and 9. It does not matter either way. 5 times 9, 9 times 5, or 3 times 15, all of that is fine. Okay? Does that make sense? So we could have done something else. 9 times 5 was the first thing I heard. That's why I went with it. It's just whatever you think at first or makes the most sense. But not the 1. Okay? We good? Yes, sir. And 3? What about? No, they are not. Because if I did that, 45, I'm going to get 15 and 3, right? And then 15 is 3 times 5. So although my tree looks different, I still have 2 3s and a 5. Does that make sense? And so your factors of 45, there's 3 times 3 times 5 in whatever order is going to give you 45. So no matter if we start differently, in the end, our trees may look different, but our endpoints of our branches should all be the same. Okay, does that make sense? All right, so let's simplify some. We're going to start with, now again, I realize that you may be able to do the first couple that I'm doing with a shortcut or in your head without doing anything. I usually start with super simple ones so we can look at process and you're not lost in the weird numbers. So kind of ignore that. Don't think I don't even need to pay attention because I already knew that answer, because I'm showing you a process within an easy one. All right, so we've got the square root of 27. So we're going to start by doing our factor tree. 2 numbers that multiply to give me 27 are what? Okay, 3 and 9. So 3 and 9 or 9 and 3, doesn't matter. I'm going to circle my 3. It's a prime number. Then 9 is 3 and 3. Okay. So I've just done the factor tree just like we did on 45. Okay. So now we're going to have to use that to help us simplify. So do you know how to play Go Fish? Okay, so if we're playing cards and I have my hand of cards and I say, do you have any 5s? And you either say yes and you give it to me, or you say no and you say go fish. So I go fish and I draw a 5. Well, now I can pair that up with the 5 that I have and take it out, and it counts as 1 pair of 5s that I took out of my hand. Does that make sense? So basically, you're playing Go Fish here. You're looking for pairs. And I've got 2 3s. I can mark this one and this one, so it gets to come out as a pair of 3s. This one has to stay in my hand because it doesn't have a pair, so he stays under the square root like that. Okay? Well, thank you. Well, they won't always be next to each other. Oh, you can, but they may be all over the place. And you don't want to necessarily be lost in trying to pair them up while you're doing it. It's almost better just to ignore whatever you're getting right there and just do it and then go back and look at them. Otherwise, you might be circling the wrong thing. It's not necessarily wrong. Like I said, there's different ways. And if that makes sense to you and you can do that, I'm all for that. There are people that teach it instead of doing like a tree, they draw it all out this way, like all under the square root. Again, there's nothing wrong with that. It's not wrong. But when your number is really, really big and you have 12 factors underneath there, that's going to get a little much. It just makes it a lot more difficult for you to keep up with stuff by doing the tree. And then notice as I used them, I marked them out so that you don't accidentally use them again. Again, this is a small number with just a few factors. But when you have a ton of them, you can get lost in your own stuff, especially if you can't read your own handwriting. So what we've done is simplified this. It's just like reducing a fraction. If I say reduce the fraction that's 4/8 and you tell me it's 1/2, well, 1/2 and 4/8 look totally different, but do they have the same value? Yes, and so do these two things right here. A couple of ways you can check yourself. When you're done, if you take what's on the outside and you square it, and then you multiply it by what's on the inside, so 3 squared is 9 times 3 is 27, and that way you know you haven't left off anything or used a number twice or whatever. Another way is if the calculator is not going to take you from here to here, but if you have one in front of you, if you find the square root of 27 and whatever that decimal is, and 3 square root of 3 and whatever that decimal is, the decimals should match. So like the decimals don't help you any, but you can see if the values match, then you know that you're good. Okay, does that make sense? All right, so let's look at another one. We're going to do square root of 24. All right, so what's your name? Elijah. Give me 2 factors of 24. Okay, 8 and 3. We'll go with that because that's what Elijah said. Could I have used 6 and 4? Yeah. Could I have used 2 and 12? Are any of those better than the rest? Yeah. No, it's just whatever pops. Yeah, whatever one you were thinking is what was the best, right? All right, so 3 is a prime number. 8 is going to be 2 and 4. 2 is a prime number. 4 and 4, so that's 2 and 2. And I'm done with my tree. Okay? So then I start looking for pairs. This 2, even though these two are next to each other, you can pair them, that's fine. But this 2 goes with this 2, so I get to bring a 2 out front. Just one 2, not 2 of them. Remember, it's coming out as a pair, like you're going playing Go Fish. Then I have left in my hand of cards a 2 and a 3. Do I get to pull any more pairs out? No. So this 2 and the 3 stay inside. Everything that's happening is multiplication, so I don't leave it like that. I'm not 100% done. That is equal to 2 square root of 6. So what is underneath the square root sign may not be a prime number. But when you split it up, there's no pairs of prime numbers you can pull out. Does that make sense to you? We good? All right. Now, how many of you were taught to look for the biggest perfect square that divides into the number? Okay. Now, and that's the one that concerns me. It's not wrong. Let me say that again. It is not wrong. And that is a good thing. And so like here, if I knew that the biggest perfect square that multiplied into or divided into there's 4. So I've got 4 times 6. Well, you still got to check the 6. That's just a 2 and 3. So you take the square root of 4. That's where you come from. And the same thing will happen there. That's fine. So let's keep that in mind. And I want to look at the next one. And I deliberately didn't write them on here because I don't want you getting ahead of me. All right, we're going to find the square root of 336. All right, quick. Give me the biggest perfect square that divides into 336. Yeah, that's what I thought. Okay? Stop. Shh. No. I didn't say a perfect square. I said the biggest because that's the only way that shortcut works. If you don't know it, don't waste a single second trying to figure it out because you are wasting your time. Because you are going to spend more time guessing and checking with numbers trying to find the biggest perfect square than somebody that just did the tree and was done 5 minutes ago. You with me? So on the little ones where you can see it and you can recognize it, that's great if you can do it that way. This is not where you want to do that. This is not where you want to stretch it out like this because you're going to have a lot of factors and you're going to double things when you shouldn't and it's going to be yucky. All right, so this kind, when they get this bad, that's when the tree really, really comes in handy. All right, so let's just think about this. Now, do you, off the top of your head, now I know I've given you time to think. If you had to think about it at all, then I don't want to know. But do you even know any factors of 336? 2 because it's even, right? And that's where you start. Don't start trying to find the biggest, okay? Would that cut down your work? In the end, not really. But at the same time, you just start knocking it down and making it smaller as you can do it like that. But we're not even going to use 2. Raise your hand if you do not know how to just look at a number and know if it's divisible by 3. And be honest, because it's okay. I always have some, and it always baffles me that nobody ever taught you. Okay. So if to look at a number without, and I mean without guessing and trying it. When you look at this, you look at the digits and you add them up. 3 plus 3 is 6 plus 6 is 12. Is 12 divisible by 3? Yes, then 336 is divisible by 3. Okay? Does that make sense? I just blew his mind. What? It works for 9 too, but only works for 3 and 9. But those are tricks that I would hope somebody had shown you along the way, but I know that's not always the case. That way you're not always guessing and checking with numbers. Should you be showing your work? Yes. Should you have like insane scratch work all over the place for things like, does this divide? Does this divide? No. There are better ways for all of that, and I will help you with those things, but you got to be open to listening to that. So we're going to use 3 just because I wanted to talk about that rule. And so then how many times does 3 go into 336? 112. That's a pretty easy one, right? All right, now, is 112 divisible by 3? No, because 1 plus 1 plus 2 is 4, so it's not divisible by 3. I don't even have to try. What is it divisible by, though, that we know? 2 and 4. Okay, I'm going to start with 2, because 4 might be something that somebody else wouldn't be sure of. So we'll just go with 2, so we can just get it down farther. But it wouldn't be wrong if you did 4. What's 112 divided by 2? 56. All right. 2 factors of 56. 7 and 8, or 8 and 7. It doesn't matter what order it is. So 7's a prime number. And then 8's 4 and 2. And then 2 and 2. Okay? So, see, we got lots of ends of our branches, right? There's lots of numbers here. Very easy to get lost in that if you can't read your own handwriting or if you have it stretched out like this or whatever else, okay? And that's why, again, this is why I'm saying along the way you don't want to worry about which ones can you put together. Just do it and be done with it. So now we look for pairs. All right, well, I got a 2 here and a 2 here, so that comes out as a pair of 2s. I have a 2 here and a 2 here. That comes out as a pair of 2s. Does the 7 have anything to pair up with? No. Does the 3? No. So it's 7 times 3 in here. Then you multiply everything outside together, everything inside together. You get 4 square root of 21. Okay? All right, questions? Now let's talk about the biggest perfect square thing. Again, this isn't a number that I would suggest doing that on. And if nobody ever said those words to you, the biggest perfect square, I wouldn't start there. That's not the way you should start. You should start understanding the tree and how it all works, and then you just kind of learn to get to that point. But the square root of 336, what I know now from this is 2 factors are 16 and 21, right? Since this is a perfect square, or any time you actually get to a perfect square, you can stop. You got to know how to handle it correctly, but you can stop. This is 3 and 7. So I don't even worry about how this relates to this anymore, because if I stop, it doesn't have anything to do with the rest. 3 and 7, I can't pull anything back out, so I know 21 stays underneath. You take the square root of that perfect square, that's where that comes from, and that stays underneath. But that's if you happen to know 16 divided in there. None of y'all knew that, and that's okay. Why would you? You wouldn't know that. But even here, I could have stopped here, and then when I took stuff out, this is a pair of 2s, and then I take the square root of that. But if you start that too soon, you start to get confused when you square root and when you just take one out and that sort of thing. You get yourself mixed up before you actually understand it. So do not start trying to do any shortcuts. The shortcuts, you'll just kind of see them yourself after you do this a lot, because you'll be doing this a lot, okay? Now, all the numbers are not big and horrible like that. I use a big one on purpose for the people that don't want to listen and always think, well, I can just use the biggest perfect square. If you know it, yes, but you're not always going to know it, okay? Any questions about any of that so far? Good? Okay. So now, let's see. I'm going to do 4 times the square root of 48. We're going to look at one where there's a number on the outside already. Okay. So when that happens, this guy that's out here, he just sits and waits. Okay, he's just going to hang out while we take care of the square root of 48. So we ignore the 4 that's out here, and we just do 48 like we would do the rest. What's your name? Fernando, give me 2 factors of 48. 8 and 6. All right, so 8 and 6, could I have used 4 and 12? But I didn't because he yelled it out. Can I use 2 and 24? Could I use 1 and 48? No. Okay. So 8 and 6. Are either one of these prime? No. So this becomes 2 and 3. This becomes 2 and 4. And then that becomes 2 and 2. Okay? So I've got my tree done. I can't forget that that 4 is sitting out there waiting on us, right? So he's going to come down here now to right here, and that's where this 4 comes from. Then I start looking for pairs. These 2's come out with that 4 as a regular 2. These 2's, 2 of them I cancel out, also come out as a regular 2. Do I have anything to pair this up with? No. Do you see why you need to circle them so you don't get lost in the other ones, and why you need to mark them out as you go? Square root of 3. And then never leave it like that. Just remember it's all multiplication, so you don't get 422 times the square root of 3. It's 4 times 2 is 8 times 2 is 16 square root of 3. Okay? We good? Any questions? All right. So I know that radicals are part of Algebra 1 again. What I don't really know, because I haven't taken the time to go figure out, is like how far you go with them. So I know that all should be a review because you at the very least simplify it, but there's a lot more to it. So this may or may not be a review for you. I'm not sure. All right, so when you multiply radicals, you can multiply everything outside the radicals together and everything inside the radicals together. And that can look a few different ways. So we're going to look at the different scenarios that pop up here. So say we start with the square root of 2 times the square root of 6. Okay? Now, first you might want to look at, could I even simplify either one of these? Well, I know I can't simplify this one, and then that's just 2 times 3, so I can't take anything out. But this gives me the square root of 12, because I can just multiply everything underneath it together. Then you try and simplify it if you can. So I'm going to do my tree, but I'm going to do it sideways. So we'll use 3 and 4. And then 4 becomes 2 and 2, which means the square root of 12 is 2 square root of 3. Everybody okay with that? So always try and simplify it at the end. It's just like fractions. They should always be reduced all the way. Always. With square roots, they should always be simplified all the way. It's the same thing. All right. Here's another thing that can come up. Square root of 5 times the square root of 5. What does that give you? Square root of 25. And then what's the square root of 25? 5. Is it plus or minus? No, because we're not solving for x, remember? If you're solving it, you're taking the square root of both sides, then you get the plus or minus. If it's just the square root of 25, we only think about the principal root. But here's the thing with this, because this kind of thing comes up a lot. This step, you skip from now on. No more of this. So if I ask you what the square root of 5 times the square root of 5 is, the answer is not the square root of 25. It is 5. Okay? The square root of 10 times the square root of 10 is what? 10. The square root of a million times the square root of a million is a million. Square root of a monkey times the square root of a monkey is a monkey. It doesn't even have to make sense to you, okay? I use monkey and elephant examples a lot because y'all seem to think that just because you're in geometry or because it has square roots in it and it's different, that all the rules in the entire world have changed, and that's not the case. A square root times itself is what you get underneath, and this is why. Because if I did square root of a monkey times the square root of a monkey is the square root of a monkey squared, and then that would still give me the monkey. But so you don't have to understand the complicated stuff. Don't let that stuff trip you up, okay? So this step gets skipped now. Then I also want you to think about this. If I get the square root of 3 squared, when you square something, isn't that just like multiplying it by itself? So the square root of 3 times the square root of 3 is 3. And so the square root of 3 squared is just 3. Square root of a monkey squared is a monkey. That's it. Okay? That comes up a lot also because these are inverses of each other. If I took x and I added 5, then I subtracted 5, aren't I right back at x? So if I take 3 and then I square it and then I take the square root of it, I'm right back at 3. So you're doing something and then undoing it. It's like using the undo button. Okay, we good? Control Z. It's my favorite buttons on the computer, because I have to undo my mistakes all the time. Along with this, another way to look at this one right here is that you've got the square root of 2 times the square root of 6. This is the same as the square root of 2 times the square root of 2 times the square root of 3, right? Because isn't the square root of 6 just that? So when you think of it split up like that, square root of 2 times the square root of 2 is 2, and then you automatically get that 2 square root of 3. So if you can learn how to manipulate the things, you make your life a little bit easier when you can kind of see how the numbers work together. Okay, we good? All right. Then we're going to do 2 square root of 3 times 4 square root of 5. So remember, we can multiply everything outside together, everything inside together, because they don't get along very well. So I just multiply 2 times 4 and get 8, 3 times 5 and get 15. And then I try and simplify it if I can. What are the factors of 15? 3 and 5. Can I take a pair out? No, so it just has to stay 15. Okay, does that make sense? If you could, then you would take it out and you'd multiply by the 8 like we did on that one up there. Questions? All right, so then we have 3 square root of 7 squared. All right. So when you square something, what does that mean? You multiply it by itself, right? Or if you have it, if this is your power of a product rule, you would square everything that's in there. We're going to look at it that way too. So this is the same thing as 3 square root of 7 times 3 square root of 7. All right. So 3 times 3 is 9. Square root of 7 times the square root of 7 is 7. So you get 63. No, you do just square it, but it's this. What do you mean that is 7 times? It's the square root of 7 times the square root of 7. Because look, let me write this a different way. Look, okay, hang on, everybody. Shh. When you square something, whatever it is, you multiply it by itself. So that's what's happening here. This times this. That's whatever this is. You take this thing, you multiply it by itself, right? No, because this is the square root of 7. Does that make sense? You can also, because I think where your brain's going is another way you could write this. Somebody said over here, it's the power of a product rule. And if I have this, then I can write this as 3 squared times the square root of 7 squared, right? Like if I had 3x squared, isn't that just, oh, not this one. Didn't that just become 9x squared because you square both of them? Same thing here. Okay, so you can write it either way. It means this, you're doing the same thing. So then when I get here, 3 squared is 9. Square root of 7 squared is 7. So you're multiplying the square root of 7 times itself, not the 7. Okay. So whichever way makes more sense to you to think about, some of you need to write it out. This kind of thing comes up a lot. It gets missed a lot. One of the main reasons it gets missed is because you do it on the calculator even when I tell you not to, and then you don't type it in right. But the calculator said it was the answer, so it must be right. It's like gospel if the calculator said it, but it's only as intelligent as the person pushing the buttons. Yes. Oh, no, but I know you use them outside of class. No. Okay. Okay, good. Good. Then that's going to help you. But for the most part, people do anyway, like I'm stupid. Like you could do the homework, and then I ask you to do it, and you can't add 2 plus 3, right? So, whatever. All right. Here we go. All right. When adding and subtracting, so when adding and subtracting radicals, always treat them like variables. Okay? If you think about them as variables, remember, don't start making stuff up because it looks different. Radicals look different. They make things look very difficult. But that's not it. It's just different, and it's pushing you outside of your comfort zone. You have to tell yourself, don't freak out. It just looks hard, and it's not, okay? So if I give you this, and again, some of you may or may not have actually added this before, but you also may have just done it wrong every time. Who knows? We got 2 square root of 3 plus 3 square root of 5 plus 4 square root of 3. Now, here's what I mean by treat them like variables. We're literally going to change it right now. I don't want you changing it every time you ever do it. Pretty much just this once for the notes so that you get what I'm trying to say. I could rewrite this. Like if this freaks you out and you're like, I don't know what the heck to do with that. If I change this to 2x plus 3y plus 4x, does that, what's in orange, freak you out? Like, that's easy, right? Do you see how all I did was take x and replace the square root of 3's? Because basically they just have different variables on them if you think of it that way. Yes. Oh, yeah. Oh, okay, gotcha. So if I were to add this, isn't this just 6x plus 3y? You think of these as things. I have 2 square roots of 3 plus 4 square roots of 3. That gives me 6 of them. It's like kindergarten. You got 2 apples plus 4 apples gives you 6 apples and 3 oranges. That's all that's happening. Okay? So this just gives me 6 apples, which is really square root of 3, plus 3 oranges, which is really square root of 5. Just like the variables are things. I have 2 of these x's. I'm going to get 4 more of the x's. That's a total of 6 x's and 3 y's. Does that make sense? Okay. These have to have, part is like a variable. They have to be the same. So you're combining like terms. And if you think of them as things, because some people actually say it this way, is 2 square roots of 3 plus 3 square roots of 5 plus 4 square roots of 3. Well, these 2 square roots are different, so I don't get to add them. But it's like giving me pencils or apples. You have 2 apples. You can add 4 more apples to get a total of 6 apples. It's like things. Does that make sense? That's why if you just think about them like this doesn't confuse you anymore, right? You can add that and it's fine. It's the same thing. It just looks different and it looks more difficult. Okay? You can't actually add the 3's or the 5's. Right here? Is this the 3 you're talking about or this one? Oh yeah, because it was only 3 square roots of 5, so that's why that's my only y right there. You get it now? Yeah, the orange one. What do you mean like? Oh yeah. Oh yeah. Right, and you just add the like square roots. Just make sure you don't do anything with what's underneath there. These square roots are just along for the ride, just like x and y are when you do this. Does that make sense? They're just stuck along there, and you just add them, and it's the like term kind of thing. All right. So we're going to do a couple more examples on here. We got room. No, because I can't let anybody go anywhere the first or last 10 minutes. Sorry. We got 5 minutes left. 3 square root of 7 plus 2 square root of 5 plus 4 square root of 5 plus 9 square root of 7. Okay, so get that done. Yeah, go ahead and just write that down and do it. It should be quick. I'm going to pass out the homework, and then I got one more example after this, but I'm going to pass this out while you write that down, because I know I'm in the way. Whatever you wrote on your calendar. That's why you have a calendar. So. Oh, you'll be here. Yeah, if you want to, yes. If you need to. I just didn't want anybody to feel like they had to every time. Yes. And then you'll get to a point where you feel like you don't need to anymore. Okay. So just hang on to this because we're not done with the notes yet. The football game in the morning? Okay. Just in the interest of time here, I get to add like terms here, this and this, right? So how many square roots of 7 do I end up with? 12. 12 square root of 7 plus 6 square root of 5. And it doesn't matter what order they're in. If this came first, that'd be fine. Okay? But there's my answer. All right, one more example. Got negative 3 square root of 8 plus 2 square root of 18 minus the square root of 12. Okay? Now, do I have any like square roots here? No. Can they be simplified? Yes. So that's what we're going to do here. We'll start with this one. So I've got, remember this 3, he just waits a little bit. So 8 is 4 and 2. 4 is 2 and 2. Right? So this negative 3 comes out, and then these 2's are a 2, and he stays underneath. So that's going to give me negative 6 square root of 2. Does So there's my first term that's simplified. Right? Now he's just going to wait there until we do the rest. Then I've got, he waits. This can be 9, oh sorry, I already wrote 9 and 2, but 3 and 6 is fine. Then 3 and 3. Right? Then remember, you got to bring this 2 down. So this is 2 times these 2 3s come out as a 3. This 2 stays underneath. So I have plus 6 square root of 2. Then this 12, I'm going to use 4 and 3. That can be 2 and 2. So those 2's are a 2, square root of 3. Now, the negative 6 square root of 2 and 6 square root of 2, what happens with them? They cancel out. They zero each other out. So is my answer 2 square root of 3? Negative. Got this negative. Don't forget to bring that down. It is negative 2 square root of 3. That's your final answer because those cancel out. Okay? Questions? Use your notes. Now listen, if you can already look at some of these and just know the answer, I'm proud of you. Good job. But you're still going to have to show me some work. You don't have to show every bit of work if you don't need to, but you got to show me something. So I don't think you're just writing the answer down from somewhere. Make sense? We good? Any questions?